This lecture is about sample moments and in particularly sample means, sample variance, and sample covariance. So before we give the definitions of these moments, let's set up some other definitions. So we begin with the concept of a population. So a population is simply a set of similar items. That could be, for example, all individuals in Sweden or all firms in Europe. So we simply think of population as a set, which we illustrate with a blob like this. So this is my population. And it contains items, and items can be sort of pretty much anything. And individual items in the population, we just denote that with a small point like that. So if this is the population of all individuals in Sweden, this is one individual in Sweden, perhaps me. Next, we define a sample simply as a set of data selected from this population. So it is really a subset of the population. And I have to define some kind of a procedure to describe exactly how I am selecting my sample. For example, if I have a database with the all individuals in Sweden, then I can randomly select a number of individuals from this database, maybe 5 individuals, and that can be my sample. The idea is that I'm hoping that this smaller sample will in some respects represent the population, which is too big to investigate. We also have the concept of a random sample. And a sample is a random sample if each item in the population has the same probability of being selected into the sample. For example, if my big population has n individuals, for example, the population of Sweden, and I need to select a sample of size small n. If I then just create a routine which picks an individual in the population with probability 1 over capital N, then I can create a random sample. However, if I just simply go out and randomly pick the first n individuals I meet, then it's not going to be a random sample. Alright, so from the population I pick individuals into a, well, let's draw it smaller, a smaller sample, and this has then size small n. The individuals inside my sample here, of which there is small n, are called sample points. So let's view that. So each element in the sample, we call that a sample point. And we typically use the small n as the symbol to denote the size of the sample. And sometimes we then use capital N to denote the size of the population. So once I have a sample of, let's say, individuals in Sweden, I can measure some characteristic of this individual. For example, I might measure the yearly income of each individual in my sample for a particular year. Then we typically use the symbol small xi to denote that particular measurement of individual I, such as the income of that particular individual. And I is any number from 1 to 10, from 1 to n. We then typically collect this data in some form of a spreadsheet or something like that. So here is an example of that. Let's say my sample consists of 10 individuals, observations 1 through 10, and I have then 10 individuals and this is the measured income in some units. So the notation here is n is equal to 10 individuals. We call this I equal to 1, that's the first observation, I equal 2 for the second one, all the way down to I equal to 10 for the final individual. And the measured characteristic of each individual is denoted by xi. So the first one is denoted by x1. x1 is 225. That's the income of the first individual. x2 is 312, and so on, all the way down to x10, which is 275. So then we just use this symbol xi to denote the income of an arbitrary individual, where I is then any number between 1 and n. Even though strictly speaking my sample is the collection of individuals that I've selected from the entire population, but we tend to sometimes denote the observations that we have, the data, these numbers x1 through xn, as the sample. But in reality they are measurements from the actual underlying sample. So from these discussions we are ready to define the sample moments. So we'll begin with the sample mean. And so given some data, measurements of my sample x1 through xn, we are going to define the sample mean simply as the sum of all the observations multiplied by 1 over n, and we're going to denote that by x with the bar on top. That's the sample mean, so we just simply sum all the xi's and divide by n. This sum here, I go from 1 to n of xi, well that's just shorthand notation for summing all these observations, x2 plus plus dot and all the way to xn. So simply summing all these numbers. This sum is denoted by I go from 1 to n xi. And then the sample mean is just this sum multiplied by 1 over n, which is of course the same thing as summing all the xi's and dividing that by n. If you want to calculate the sample mean in Excel, you can simply use the sum function, sum parentheses, and then you just highlight all the cells that you want to sum, all these guys. So that will give us the sum, and then you need to divide that by n, which is 10 in this case. So the sample mean of the income data is 259. Calculating the sample mean is so common that there is actually a function which does the division of the sum automatically, and that's called the average function. And then you just highlight the data, and with the average function you don't have to divide by 10, that's done automatically by Excel, so you get the same result. Average is another name for the sample mean. Moving on to the next sample moment, and that's the sample variance. And the sample variance is defined as follows. It too is a sum of all data, but in this case we don't sum the xi's, we sum xi minus x bar squared. And in this case we don't divide by n, we divide by n minus 1. The common symbol for the sample variance is S2, and it's also common to put the name of the variable as a subscript. So S2 with the subscript x. That will then tell us that it's the sample variance of the x data. There is obviously a function to calculate the sample variance of your data in Excel as well, and it's called VAR, variance dot s for sample, and then you just highlight your data, just like when you calculate this sum or the mean. So the sample variance is 1665.11 something. So I think it's a little bit useful to look a little closer at the sample variance formula. So the sample variance formula S to X is like this: 1 over n minus 1 summation I go from 1 to n xi minus x bar squared. The symbol inside the parenthesis xi minus x bar, that's typically called the deviation from the mean. Deviation as it's a minus, and from the mean because we simply subtract the mean. So let's have a look at the deviation from the mean data. So in this column, I want to create the deviations from the mean. I just simply want to take the income and subtract the sample mean. A nice way of doing that is to name the sample mean using the name cell here. So let's just call that, let's call it x bar. That's my sample mean. And now I can just refer to x bar in my formula. So here I need to calculate income of individual 1, 225, and I want to subtract 259. But I want to do this in a general way, not using the numbers, so I can copy the formula down. Formulas in Excel always starts with an equal sign. So equal the income of individual I, that's in cell B2, subtract from that the x mean. Well, I call it x bar actually. Subtract from that x bar, and that's the deviation from the mean for the first observation, for the first individual. So think of this number simply as this guy has an income which is 34 units below the average. So with Excel, I don't have to copy and write this formula for all these individuals. I can just use this fill handle and just drag it down, and that will give me the deviations from the mean for all individuals. The second person had an income of 312, has an income which is 53 units above the mean, and so on. The next step in the formula for the sample variance is that we are supposed to square the deviations from the mean. So these guys are squared. Let's abbreviate that with deviations from the mean. Square deviations from the mean. So let's calculate that in our Excel sheet. Let's just call it squared deviations. So I am simply going to square each deviation from the mean. And the square in Excel, you can just do ℏ2. That's the square. A few things to note with the square deviations. First of all, they must all be positive. Square deviation must always be positive or 0, since squaring any number will give you a non-negative result. Second, the further the income is from the mean, the larger the squared deviation. For example, for individual here, number 7, this individual had a deviation from the mean which was very small, just 5 units below the mean, and that individual's square deviation would be very small. This individual had a income which was much lower than the mean, 72 units, and therefore gets a very large square deviation. So keep this in mind. Observations that are close to the mean will give you a small square deviation, while observations that are far from the mean will give you a large square deviation. The next step in the formula for the sample variance is that we are supposed to sum all these square deviations and divide that by n-1. So we can now check that Excel has done its computation of the sample variance correctly by just doing sum of all these ones, divide that by 9, n-1 is 9. So this means that I can't take the average of these square deviations because that would divide by 10 and we need to divide by 9. So we can see that we do get the same result. With this view that the sample variance is the sum of squared deviations from the mean divided by n-1 can give us some intuition of what it's actually measuring. So here are two cases. In the first case, I have a sample of 10 individuals. In the second case, I also have a sample of 10 individuals. These are the incomes in my first sample, the incomes in my next sample. The sample mean of my first sample is 259. That's the average of these numbers. And the second sample has the same sample mean, 259. But if you look at the first sample, the deviations from the mean are very small. This one, 259, of course, then the deviation is 0. It's right at the mean. 262, the deviation is 3. So this sample has very small deviations from the mean. That means that all income data are very sort of close together, and they're close together to the sample mean. That since these deviations are small, the square deviations are also small, and that in turn means that the sample variance for this data is very small, 4.4. In the second sample, I have exactly the same sample mean. The average income of these individuals is the same, 259. But in this case, the spread is very large. The individuals have income which are really far from the mean. This guy has 108 units above this mean, and this guy has an income which is 157 units below the mean. Much bigger deviations. And squaring these deviations will then give you very big numbers, and that in turn will give you a very large sample variance. So a large sample variance is consistent with large deviations from the mean, which means that the spread of the data is much larger. The spread of this income data is much larger. A small sample variance is consistent with small deviations from the mean and a data set which has a very small spread. Another way of illustrating this is to look at the income data. So if I look at this data, the first sample, and the data from the second sample, and I do an insert, and I do just this. Then the blue line is from the first series, the sample with the small sample variance, and you can see that there is very little variation in the income. While the orange one is the data from the second sample where there is more variation in the data. So the orange data has a higher sample variance. Although the sample mean is the same, they have different sample variances. So from the sample variance, we can also define a concept called the sample standard deviation. And the sample standard deviation is simply the square root of the sample variance. The notation we use is S instead of S square. And since the sample variance is the sum of non-negative numbers, the sample variance can never be negative, so it's always safe to take the square root of it. So to get the sample standard deviation, we can just take the square root, and that's SQRT in Excel of this guy, sample variance. So the sample standard deviation is 40.8. Of course, that too is built into Excel, and it's called STDEV, standard deviation dot S for sample. But then you have to mark up the income data like that, and that gives you the same number. So moving on to the third sample moment, the sample covariance. First of all, if I have a sample drawn from a population, I can actually make more than one measurement from each observation. So let's say I have a sample of firms, for example, drawn from some population. Then I can make, let's say, 2 distinct measurements for each firm. Say, for example, I could measure the total revenue and also the total cost for each firm. In that case, I typically use the symbols X and Y. So I have a population, I make 2 distinct measurements from each sample point, and I'm going to denote them by Xi and Yi. So Xi and Yi are always connected in the sense that they refer to the same sample point, but they are indeed different measurements. So in this case, I have data that looks like this. I have data on an X variable, such as revenue, and I have data on an Y variable, such as cost. In this case, my data could look something like this. I have 10 firms, n equal to 10, and this is the revenue data, revenue for the first firm and so on, and this is the cost data, cost for the first firm. I denote one by using the symbol X and the other one using the symbol Y, and I just pick these arbitrary right now, makes no difference. So for example, this number here, 62, that's my X1, that's 62, and this number here, that's my Y1, that's 31, and so on. This is the X10 or Xn, if you like, because n is 10 in this case. So given data on 2 variables, I can define the sample covariance, and the formula for the sample covariance is like this. If we look inside the sum, we recognize the first parenthesis as the deviations from the mean for the X variable, and the second parenthesis as the deviations from the mean for the Y variables. And we take a product of those and sum them and divide the whole thing by n minus 1. That's the sample covariance. To calculate the sample covariance in Excel, you just do covariance dot s for sample. Then, as you can see from the hint, it needs 2 arrays, the array of each of the variables. So we'll do revenue as the first, and then we'll do cost as the second. It makes no difference in which order you do this. So the sample covariance between cost and revenue comes out to be 137.5. So again, let's develop some intuition of what the sample covariance measures by just looking at the formula. So the sample covariance, which we denote by x and y square 1 by n minus 1, summation, I go from 1 to n, xi minus x bar times yi minus y bar. So let's do these two in one column each, the deviations from the mean. So I need the average of the x data and of the y data. Average of the x data and average of the y data. I name them X bar, and I name, well, I can't use X bar, I already used that in a previous sheet, so let's name it bar X, and I name this bar Y. In the name cell, bar Y. Then let's do deviations from the mean. So dev X will be deviation from mean in the X variable, which is revenue, and this will be deviations from the mean in the cost. So this is revenue minus bar X. Copy this down, and this is the cost minus bar Y, and copy this down. So the following here is important. If you look at the deviations from the mean, they tend to have the same sign. For example, for the first observation, they were both positive, both negative, both positive, and so on. If you think about that, that's not too surprising because, for example, for the third observation, we have a high revenue, 84, 20, almost 25 units above the mean. Well, that sort of signals that this is a pretty large company, and you would expect the cost to be pretty high as well, at least above the average, and it is above the average. While on the other hand, let's say this observation number 7, very small revenue, very small cost, so this is a much smaller firm, so the deviation from the mean tend to be negative, both of them. But of course it doesn't have to happen. For example, for this guy, the revenue is slightly below the mean, while the cost is slightly above the mean. In the next step of the formula for the sample covariance, these deviations from means are supposed to be multiplied. So let's do that. Let's multiply the deviations from the mean. So it's this multiplied by this. Copy this down. And the important thing to note here is that since the deviations from the mean tend to have the same sign, plus in this case, the product tend to be positive. Product of two positive numbers is positive. The product of two negative numbers is positive as well. So they all tend to be positive. There's one exception here with a small negative number, because for that observation they did have a different signs. But they tend to be positive, so that when you sum all of these numbers, you end up with a positive number. So let's check that Excel calculates the sample covariance correctly. Supposed to be the sum of all these numbers, and then check the formula, the sum of all these products, and divide that by n minus 1. Divide by 9, and hopefully we get 137.5, and we do indeed get that. Another way of illustrating this positive sign of the sample covariance is by looking at the scatter plot of revenue and cost. So if I just mark revenue and cost, and I go to insert, and I pick the scatter plot instead, like this, we can see that each point now represent each firm. So for example, this guy down here is 3616, so that is observation firm number 7, and so on. And since costs tend to be lower when revenue is lower, we have small firms here and we have big firms here, we see that there's a tendency for these points to move upwards as I move to the right. But the covariance can also be negative. Consider this simple example. I again have 10 observations. This is my X data. It grows from 1 to 10, while my Y data decreases from 10 to 1. Both X and Y has a sample mean of 5.5. So if you look at the deviations from the mean, X goes from minus 4.5, this is 4.5 below 5.5, up to 4.5. While for the Y data, it's the opposite. This goes from 4.5, 10 is 4.5 above 5.5, down to minus 4.5. Now in this case, each observation tend to have a different sign for each deviation from the mean. Actually, that happens in each case here. So when you take the product of these two deviations, you will always get a negative number. And summing up all these negative numbers will give you a negative number, so the sample covariance is negative. And we can illustrate that too by looking at the scatter plot of X and Y. So let's do insert scatter plot X and Y like that. In this case, they are all completely lined up on a straight line, with the first observation to the left and the last observation to the right. So remember this, if the sample covariance is negative, as it is in this case, it simply means that whenever X is above its sample mean, that is down here, then Y tends to be below its sample mean over here. Whenever X is below its sample mean, Y tends to be above its sample mean. In that case, the sample covariance is negative. And the sample covariance can also be 0. For example, if I change all the Y data to 5 like this, then the sample mean is 5, and all the deviations from the sample means for the Y data is 0. They're all equal to the sample mean. So when you take the product of the deviations from X and the deviations from Y, you will get a 0. And summing zeros, you get a 0, and the sample covariance is 0. So in this particular case, there is no sample covariance. Now, of course, this is not the only case when the sample covariance is 0, when the Y data is constant. If I change this to a 4 and this to a 4, for example, such that this is below the mean and this is above the mean for Y, you're still going to get the sample covariance of 0, because there is no tendency for these points to go upwards or downwards. Finally, we have a concept closely related to the sample covariance, which is the sample correlation. The sample correlation is denoted by R. Then we use subscript X and Y to denote that it's the sample correlation between the X and the Y variable, and a square just like in the sample covariance. And the definition is that it's a ratio of the sample covariance, and in the denominator we have the product of the sample standard deviation for X and the Y data. So to calculate the sample correlation, we calculate the sample standard deviation. So that's STD ab sample for the X data. Then we do the same thing for the Y data. And that will allow us to calculate this sample correlation simply as the sample covariance divided by the product of the standard deviation, 0.966. So the sample correlation always have the same sign as the sample covariance, but it's normalized in the sense that it will always lie between -1 and 1. You can, of course, calculate the sample correlation directly in Excel using the Corel function. So you do Corel, and then you just do the x data, comma, the y data. And that also gives you 0.9666.